Okay, as promised, we're going to go through a steady state approximation example, and I'm also going to do a little review with you on significant figures, just trying to wrap up all those little odds and ends. So when do we have to worry about steady state approximation? The only time that this comes up is when we have a multi-step or a multi-step reaction with a slow step being the second step. So here's the problem that you run into. We could write rate laws for each of the steps. Here's our rate law for step 1 and for step 2. And for the overall reaction, in most cases we use the slow step to represent the rate of this multi-step reaction. Do you see a problem with this rate law though? Well, hopefully you recognize that one of the things in this rate law, the N2O2, is actually an intermediate. And that's a problem because we can't have an intermediate inside of our rate law. So what we're going to do is we're basically going to replace N2O2 with what it's equal to from the first rate. So taking the rate of the first reaction, the forward reaction, and just writing it again, we know that at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. That's what this is. Take a second, recognize that the second law here that's given to you is the reverse process going this direction, where we're using k-1 just to represent the k value for the reverse process. Now we have, because we have this equation here, now we have this relationship between NO and N2O2, which is an intermediate. We're going to rearrange and we're going to get N2O2 by itself. Take a second, just verify the algebra that's going on there. The nice part about solving for N2O2 using this first step of the reaction is now we can replace our intermediate with what it's equal to. So we're going to take this rate, the rate law for the second reaction. We're going to write it again, but instead of N2O2, we're going to replace N2O2 with this here. That's going to replace that N2O2 intermediate, and you end up with this rate. You know, it looks complicated, but it's all just algebra, right? We replaced N2O2 with K1 over K negative 1 sub negative 1 NO squared. And we could further simplify this. If the question asks us to further simplify this with a single k, I'm actually going to replace the one they have. I don't like the way it's written. We could further replace it by saying that k2 times k1 times k1 over k negative 1 there. We could say that this is a different k value. We'll call it k3. If that's the case, then we're just going to replace it with k3, and this reaction becomes k3 with NO squared times O2. That is our rate law for the reaction that we saw above without including an intermediate. So again, what is steady state approximation? It's taking the rate law for the slow step and replacing the intermediate with what the intermediate is equal to from a different step. We use step 1 in this case, and we solved for N2O2 and replaced it. Okay, now on to our little sig fig practice here. Remember that with addition and subtraction problems, we use different rules than we would use with multiplication division. The one that we use most frequently in chemistry is multiplication division. Those style of calculations just come up more frequently. I'm going to start by getting an answer here. You can imagine that we have units in this problem. The calculator answer is 0.240310078, but I need to round that to something that makes sense. With multiplication division, we're going to round to the least number of sig figs. So remember that non-zeros are always significant. Sandwich zeros are significant. The only times we don't count zeros is when they're in front of a number, like those three there. So we have 1, 2, 3, 1, 2, 3. Both of these numbers have 3 sig figs, so we're going to round our answer to 3 sig figs. 1, 2, 3, and this would be equal to 0.240. Remember that this 0 here does not count as a significant figure. Try D yourself. You can pause the video if you need to try it yourself. Okay, so I'm just going to get into it now. If we do this calculation, we end up getting an answer of 2.13786. These 3 zeros are not significant, but these 3 are, and so are these 3. So our answer should be with 3 sig figs. Therefore, we should put 2.1 rounding up 4 as our answer. That's multiplication division. With addition subtraction, we're still going to round to the least significant, but we're not going to count sig figs per se. We're going to look at the decimal place. So let's get an answer first. I get an answer of 1436.996 on this one. So if we're going to round this, we need to know how precise are these numbers. 13.77 is precise to the hundredths place. This next number to the thousandths, and 515 is precise to the singles. Which of those 3 numbers would you say is least precise? Well, it's the singles place. So that means that I need to round to the singles place. And the answer that I would get here would be 1437, because that would round up there. If you want to put the decimal place in, you can do that too. All right, try C yourself. I got an answer of 156. This is precise to the 10th. This is precise to the singles. So we're going to round this to the singles place, and it would be 156. Now this question goes a step further. It does say express these using scientific notation. Of course, we could do that too. If you want to pause the video, try it yourself. For this first one, I got 2.40 times 10 to the negative 1. And it's got to be 2.40 because that's got 3 sig figs like our answer here. Down here, it would be 2.14 times 10 to the 0 power. For 156, it'd be 1.56 times 10 to the second. And here would be 1.437 times 10 to the third.